Today, we want to drop back to the fundamental theorem of calculus and look at the structure that's contained in the fundamental theorem of calculus. We know that there are two parts. One part that says we can calculate a definite integral with an antiderivative, like we have here. We're calculating a definite integral using an antiderivative. Notice that I've shifted that a little bit. Instead of integrate a function to the antiderivative, I'm integrating the derivative function. But the function is an antiderivative of its derivative, so that's the whole. The other part of the fundamental theorem of calculus says that we can use a definite integral to construct an antiderivative. So those are the two pieces that are going on in our original fundamental theorem of calculus: the definite integral and the antiderivative. Part one, you can use an antiderivative to calculate a definite integral. Part two, you can use the definite integral to construct an antiderivative. That's the relationship. I want to look at that first part, integrating a derivative. So what we're doing is we're integrating f prime over the interval from a to b. We're integrating f prime what we're doing is we're integrating the derivative of a function over an interval. We're integrating the derivative of a function over an interval from a to b. And the fundamental theorem of calculus says that we can calculate this integral by evaluating the function at the endpoints of the interval. So we're evaluating the function as the difference in the we evaluate the definite integral as difference in the function at the endpoint of the interval. When we look at that, we're calculating the difference in the function evaluated at the endpoints of the interval. Whatever is going on in between, in the interior of the interval, we care about the function evaluated at the endpoints of the interval. We're concerned with what's going on at the boundary of the interval. We integrate a derivative by evaluating a function at the boundary. We integrate the derivative over an interval by evaluating the function at the boundary of the interval. we integrate the derivative f prime over an interval from a to b by evaluating the function f at the boundary of the interval. Which, since we're just dealing with the interval, is just the endpoints. An old idea, we're just highlighting some new parts of it. Integrating derivative over interval by evaluating the function at the boundary of the interval. This is our new theme. Integrate a derivative over a set by evaluating the function at the boundary of the set. So, when we're in vector calculus, we need something else to stand in for the derivative. Since we're dealing with functions of more than one variable, we're going to need some partial derivatives and some way to combine them. Since we're talking about vector calculus, it's probably going to be a vector. And this is the thing that's going to stand in for the derivative. The del operator is the derivative for vector calculus. Like this one up here. This is going to be the derivative, but for vector calculus. We want to write down what the del operator is. Here is the del operator. Unsurprisingly, since I'm calling it a derivative, it's going to involve all of our partial derivatives. Partial with respect to x, partial with respect to y, and the partial with respect to z. And I made a vector out of it in kind of the most obvious way possible. The partial with respect to xi, plus the partial with respect to yj, plus the partial with respect to zk. If I said make three partial derivatives and make a vector out of it, this is probably the way that you would do it. I like it when math is just does the obvious thing. Now, you may recall that one of our alternate notations for the gradient of a function was del f. And when we apply the del operator to a scalar function, we get the gradient. When we apply the del operator to a scalar function, we get the gradient. So del f is the gradient of f. That's the partial of f with respect to xi, plus the partial of f with respect to yj, plus the partial of f with respect to zk. That's just the gradient of f. So this operator, being a vector, when we apply it to a scalar function, ends up with a vector. Since it is a vector, we can apply it to, so this is the del operator applied to a scalar function. It results in a vector that we call the gradient we talked about previously. A new kind of function that we have is a vector field, where our function is has an output that is a vector. So the other thing that we want to do is apply this to a vector field. So at this point, we are looking at a vector field, and we have this del operator, which is itself a vector. So I've got a vector, the del operator. I've got another vector, the vector field. What am I going to do to combine them? Here's a hint. I'm thinking of two ways to combine them. What are they? I got a vector over here. I got a vector over here. What am I going to do? What two things am I going to do? I got two options. I could take a vector dot a vector, or I can take a vector cross a vector. So I'm going to take a vector I can take the del operator dot the vector field, or I can take the del operator cross the vector field. We're just looking at structure. I haven't told you what these mean. We've talked about what the gradient represents relative to the function, what it means, what the gradient is telling us about the function. Here, I'm just posing that the del operator is a vector, and I want to look at how I can combine it with a vector field, a vector value function. And I got two options. I take two vectors, I can dot product them, or I can cross product them. It doesn't really make sense to add the two vectors. That's why I threw in that extra bit that there are two options. There were two things that I was thinking of combining these vectors. Because the partial with respect to x is not really a thing that I can add. Because the rules for addition state, we can only add things that are the same, and when we add them, it doesn't change what they are. It doesn't make sense to take the partial with respect to x and add it to a function. That doesn't make any sense. We don't have a way to do that. But as far as an operation goes, apply the partial with respect to x to a function, that we can do. And that's what's going on here. Remember, we think of the dot product and the cross product as a multiplication, but multiplication is more general than that. In this case, the multiplication is like a composition of functions, or applying an operator to a function. Does that make sense? That was a detail, because maybe the first thing that you thought of is like, I want to add these two vectors. But that doesn't work, because this is an operator, and that's a function, and that doesn't make sense. Addition doesn't like that. Addition only takes two things that are the same and puts them together. And when it does that, it doesn't change what they are. We say 5x plus 3x is 8x. We can add those two terms because they're the same. 5x and 3x. So we have 8x. And it didn't change what they are. They're still x's. Right? That's the intuitive nature of addition. That's the intuitive, what should be the intuitive nature of algebra. 5x plus 3x is 8x. Just like $5 plus $3 is $8. 5 pencils plus 3 pencils is 8 pencils. But when things are different, 5x plus 3y, we don't add those. X's and y's are different. $5 plus 3 pencils is not 8 of anything. Good question. So if you're thinking, can we add them? And I didn't write that down. You're like, well, why can't we add them? That's part of the reason why. One of the reasons why. But we can take del dot f and we can find del cross f. We do have names for these two things. Del dot f is known as the divergence of f. And del cross f is the curl of f. Specifically, the vector curl of f. And it makes sense that it's the vector curl of f because it's a cross product. The output from a cross product is going to be a vector. Perpendicular to the operator and the function. Yeah, that's kind of weird. It is perpendicular to the operator. That's kind of funky. We'll have to think about that. But here are the two options. So in vector calculus, it's like we've got these 3 different derivatives. The gradient, the divergence, and the curl. That's actually not the way they show up. The gradient, the curl, the divergence. So the way I want to picture this is that there are 3 different derivatives of vector calculus: the gradient, the curl, and the divergence. If we go back to our opening, the fundamental theorem of calculus, we had just, when a function of one variable, we just had that one version of the derivative. All those rules that applied to it, but it had that one derivative. And we had that one fundamental theorem of calculus relating to the definite integral and the antiderivative. Here, like we got 3 different derivatives of vector calculus. Gradient, the divergence, and the curl. The gradient is the del operator applied to a scalar function. The curl is the del operator cross the vector function, the vector field, and the divergence is the del operator dot the vector field. It's a little bit weird because our multiplication isn't quite multiplication here. Our multiplication is applying the operator partial derivative to the function. So that's a little bit weird. That's what's standing in as our multiplication. Because these operations are normally multiplication. They're called products, so there must be some kind of multiplication. Let's generalize the structure that we have from our fundamental theorem of calculus. I want to integrate some derivative over a set. We do that by evaluating the function at the boundary of the set. This is what I refer to as grossly exaggerated, grossly overgeneralized. But we're going for some kind of intuition here, and not really a mechanical computation. We're just trying to see some structure and see if that helps us. I know we've only barely talked about line integrals. The idea is we've got some vector field. It's the airflow in a room. And we've got some path that we want to run through the room, a fly flying through the room. And we want to know how much the airflow in the room is pushing the fly or working against the fly. Is the fly flying into the wind or flying with the wind? And if so, how much? That's the dot product. The dot product is telling us how much of that is happening. The fundamental theorem of calculus for line integrals is going to be the gradient one. The fundamental theorem of calculus for line integrals says the following: the integral over C of the gradient of f dot dr is f at q minus f at p, where C is any path from P to Q. So the set C is any path from P to Q. This fits our model of the structure of our fundamental theorem of calculus. The gradient is standing in as the derivative. The set over which we are integrating is this path from P to Q. The endpoints, or the boundary of that set, are the points P and Q. And that is where we are evaluating the function. The gradient of f is standing in as the derivative of the function, so the function itself is function f. P and Q, the endpoints of the path, serve as the boundary of our set. Some big deal stuff to point out here. C is any path from P to Q. C is any path from P to Q. Gradient fields are called conservative, so the path doesn't matter. Notice that we're doing this line integral over a very specific field of gradient field. If that field is the gradient of some function, then we just have to look at the endpoints, just like in our fundamental theorem of calculus. So C1 maybe is this path from P to Q. C2 could be some other path. Any path from P to Q. If you're integrating a conservative vector field, like a gradient field, then you just need to look at the endpoints. So a little bit of DVD bonus material, which is not germane to the discussion at the moment, because I haven't even talked about what a conservative field is, but a gradient field is a conservative vector field, and all conservative vector fields are gradient fields. So if you have a conservative vector field, then it must be a gradient field of some function. What we care about is the structure of our fundamental theorem of calculus, where we integrate the derivative over a set by evaluating a function at the boundary of the set. The fundamental theorem of calculus for line integrals is the gradient one. So we got two more, clearly. The curl one and the divergent. Stokes' theorem is the curl one. So just by what I've written down here, we can see the set over which we are going to be doing this integral. This is the integral of a curl of f dot dA. I've switched up from dr to dA, which means we are not going to be integrating over some curve. We're going to be integrating over some surface S. In this case, we can see that the derivative that's in play is the curl of the vector field, and that means the function in play is the vector field. We evaluate the derivative over a set by evaluating the function at the boundary of the set. So S is some surface, the boundary of which is C. So what's going on here is we've got some curve C and it's the boundary of some surface S. I don't have the budget for a hologram where it's coming out of the page, so you have to imagine this is real fun. The curl is the del cross F. So this is acting as the derivative. And our vector field is acting as the function. We're evaluating the function at all the points C. So we're calculating a line integral around the boundary C. Stokes' theorem is the curl one. Notice the structure. This is why Stokes' theorem is one of our fundamental theorems of calculus. What does this surface integral mean? That's not important. It's just the vector field flowing through the surface. That's the rough idea that we have right now. We talked about it before where dA is some vector normal to the surface. It's saying what direction the surface is going. And what's the how's the vector field flowing through that? And our third fundamental theorem of calculus in vector calculus is the divergence theorem. This is going to be the divergence one. This is also known as Gauss's theorem. But I guess this book, the authors of this book said there's too much stuff named after Gauss. That was just what, that's this kind of dude that Gauss was. Gauss is very prolific. If you were a mathematician living at the same time as Gauss, if you did something new and novel, Gauss probably has already done it first. You would write Gauss a letter, say, well, hey, Carl, check it out. Look what I found. And Carl, I don't know if you went by Carl or Freddie. I call him Freddie. He's dead now. He's not correct. But Gauss would write back, it's like, oh, yes, of course. I discovered that quite a while ago. I had forgotten about it. Thanks for reminding me. I'm like, son of a bitch, did you discover everything? He's like, well, have you discovered this yet? No? Then yes, I have. And he's very prolific. It's like you go through math and look up Cauchy and Euler and Gauss, and they're just all over the friggin' place. Part of it is because they are excellent mathematicians. The other part is timing. They showed up kind of after calculus. And showing up right after calculus, if you're willing to just like spend some time doing math, you're going to be rewarded with your name all over the place. It's like calculus was locked in this room. And Newton and Leibniz opened the door. Newton opens this door. Leibniz opens the other door over there. And then everybody just started rushing in. And first in line were Cauchy, Euler, and Gauss. I'm like, wow, look at this stuff. Cauchy, and Euler pick up the same thing at the same time. Cauchy, Euler. Do it again. Euler, Cauchy. And meanwhile, Gauss is like, oh yeah, I already found that. It was over there. What? And then he like grabs it. It's like, oh, Gauss. Son of a bitch. Meanwhile, Newton was standing in the hall kind of going crazy. So the divergence theorem remember, the divergence of F is the dot product of the dull operator and the vector field. So this is going to be a scalar. So I'm just going to multiply it by dv. And that's going to give you an idea about what kind of set we're integrating this. We're integrating the divergence of F times dv over some solid W. So W is a solid. This dv thing part says solid, just like this dA part says surface. And the boundary of the solid is a surface. And so unsurprisingly over here, we integrate the vector field over the surface S. This is a surface integral dot dA. Here the divergence is serving as the derivative and the vector field itself is the function. So W would be like the solid sphere, all the stuff inside the sphere, and the surface S would be the surface of the sphere. S would be the surface. and W will be the solid part. This is mechanically what we're talking about in the fundamental theorem of calculus. This is what we're aiming for. This is what shows up at the end. So this is kind of like a spoiler alert. This is the last chapter. So it's a little bit like a Quentin Tarantino film. You know what's supposed to happen at the end, and then you just kind of like go back. Or like the movie Memento. Has anybody seen Memento? Okay, you need to watch Memento as a movie. It's got Guy Pearce in it, and what's his name? Pantaleone, Bill Pantaleone. It's a very good movie, and it's kind of filmed backwards. So it starts at the end, kind of like builds in the beginning. But don't watch it while you got finals going on. Wait till after finals because doesn't have to remind you a bit. All right, that's going to do it for today. We'll talk more about what the del operator means, the curl, the divergence, and the gradient as we go on. That's it for today. I'll see you all on tomorrow. Have a good day, and thanks for playing. See you tomorrow.